Okay, generally this whole chunk in this video, I think I'll just focus on ADC and alliancing. I will assume that you already know what is ADC, alright, analog to digital or digital to analog. Alright, so you will convert into both worlds, analog system, infinite resolution, range, and range, because it is, it's continuous, alright, it's continuously. While in the digital, it's actually taking discretized systems, alright, taking different points, if you still remember, alright. And then from the analog to digital, you may have an error. So over here, this blue color one is your analog signal, alright, and your quantized signal is actually where's your quantized signal? Your quantized signal is actually the green color one over here, alright, while your your quantized signal is the red color one. Hold on a while. Okay, so your blue color one is your analog signal, okay, while your green color one, alright, is your sampled signal, your discretized signal, alright, while your quantized signal is the red color one, alright, because you round off. If you remember, quantized signal is you round off. Okay, so the error between them, alright, between the analog and the discretized one, if you take the analog, that's why I assume that if you take the analog minus away the digital one, what you have for this part is so over here at this particular point, they are the same. The errors aren't very much different, alright. And over here, if you take 0.8, this is 0.8, yeah, this is 0.8 somewhere, minus away 0.6 or 0.2, alright, so you have somewhere minus from 0.5 to, anyway, it's not very important, but just want to show you that this thing over here, if you minus away this thing, I think is your error at this particular point. Okay, but why the error so big? That's another thing. But this is not the case that I just want to convey to you, but at least you get a feel of it. But anyway, this is the thing that I just want to say. And then the Nyquist sampling theorem is your Shannon sampling theorem. So you talk about the Nyquist limit, alright. So for a signal which has, for example, 48 kilohertz, right, you need to divide it by 2, so you have 24 kilohertz. So you can only sample using 24 kilohertz, alright, although you use 48 kilohertz, alright, but however, because of the alliancing effect, alright, I'll not go into that because I assume you already know, I'm lazy to say, alright, the alliancing effect over here, alright, because at this point the amplitude itself, alright, this is go back all the way to digital control. In the analog system, alright, this is only one wave. In the digital system, it is considered with infinite similar wave, alright, infinite. So over here, there's a cross section over here, alright. For example, if the magnitude over here is 2, alright, so but however at this particular point there is a cross section, so it's like 2 times 2, alright, because there is 2 graph cross sectioning at the same point where the magnitude is 2. Or if you say the magnitude is 3, for example, alright, it's 3 times 2, alright, because at the cross sectional point is that, alright. So as you can see from here, you can surely know that the system has reached a higher frequency, alright. So you require a higher frequency, alright, to read a slower frequency. You get what I mean? So over here, you require a higher frequency in order to read your signal because of this alliancing effect over here. Okay, I hope. Yeah, but anyway, any time when you see sample at 48 kilohertz, you need to divide it by 2. So this divided by 2 is actually your Nyquist limit. Alright, your Nyquist limit meaning that you can only sample 24 kilohertz of data. Alright, although you sample 48 kilohertz of data because of the alliancing issue, alright, over here you can only sample 24 kilohertz only. Alright, just take note of that divided by 2 Okay, I'll not go into details of this. Talking, I just realized I may not be talking, but anyway, if you have a 200 Hz to 20 kilohertz, this is the human range of hearing. If you want to sample the human's voice, you require 400 Hz to 400 kilohertz. alright, or 40 kilo, sorry, this is 40 kilohertz. Because if you want to sample a analog system, if you want to sample anything, alright, you requires ×2 of your original signal, because of the overlapping over here. Alright, so this overlapping requires faster speed to sample, so therefore you need a ×2 faster speed to actually sample your original data. Okay, alright, hopefully yeah. Another method is you can use the anti-aliasing filter, or you can say it's a low pass filter. Alright, so you filter away this part over here, so they will not cross. As you can see, they will not cross each other at this point, because you already filter out the irrelevant point that you want to ignore. Okay, so that's why it's very clean over here. Alright, so therefore just a side note, you may actually want to spend time to think about why is it a Nyquist frequency 50 Hz, which is over here, and the sampling frequency 100 Hz over here. Alright, I would think that the Nyquist frequency is your cutoff frequency. Alright, but I just leave you to think about it. I don't think it's useful for us lah. And then alright, in many applications, the low pass filter or anti-aliasing filter are not required, because for your signals for your light and your temperature sensors are usually have no significant components at higher frequencies. Alright, so if you think about it, this is one for example, this is one part of the signal. Okay, so over here, the further you are, the higher your frequency is, right? This is the frequency domain. Alright, so therefore normally they only concentrate on the lower frequency sides. Alright, so therefore the higher frequency is not of our concerns. Alright, so therefore we will not experience any aliasing effect, because seriously, because we are only talking about low frequency only. High frequency we don't even reach there yet. Alright, so therefore we don't even need any form of so-called emulation, or any form of a method to actually solve the aliasing, because in order for aliasing to occur, you need to be at least 50 Hz. But if normally your working frequency is only at 20 Hz, alright, you don't even need to go into 50 Hz at all. So definitely the aliasing effect will not affect you, and this is why they are trying to tell you that lah. Alright, so for light and temperature sensors, normally you will not operate in high frequencies, and therefore you don't need to use anti-aliasing filter. Alright, and then so imagine if you have a 4-bit system. Let's talk about the quantization. Okay, and you want to model a 1 volt. Alright, this is 0.5 volt. Alright, for a 4-bit system, alright, you actually break down into 0, 0, 0, 0, and then 0, 0, 1, 0, etc. Alright, so each of the blah 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 blah, each of this binary contain each of the voltages. So you'll split into, so 1 volt will split into 8, so it's 0.125. So each of the binary, this is 0, this is 0.125, this is 0.25, this is 0.375, etc. all the way. Alright, so this is a form of quantization. Alright, so therefore the higher number of bit you have, alright, the better quantization resolution, because you can actually have more fine voltage. Alright, so because for example 1 volt divided by 50, so you'll have what, 0.02 volts. Alright, compared to 0.125, 0.02 is much fine, or much more precise, because you are going into intervals of 0.02. This one is 0.125. Alright, if it's like for example 1 volt divided by 1 bit, then it's just 1 bit 1 volt. Alright, either 1 volt or 0 volt, that's all. Alright, if it's a 4-bit system, alright, it can be 1 volt, can be 0 point something something, 0 point something for different 8 values. Alright, so you can actually break down a 1 volt into many possible values. Alright, so you can vary between 1 volt and 0 volt. Alright, nonetheless, if you want more accurate one, you can have more variations, so that you can better control your stuff, or whatever thing that you want. So it's better resolution, so to speak lah. Okay, so it's trying to say about that. Alright, the resolution is defined by the number of bits used to used to represent the signal. Alright, where the number of levels 2 to the power of n. So 2 to the power of 4 is 4 bit, 2 to the power of 8 is 8 bit, 32 2 to the power of 32 is actually 32 bits. So this is how it's talking about it. Okay, so in order to find the quantization resolution, did I say that if it's 4 bit, alright, it should be 16 possible values. Alright, 16 possible values, 0, 0, 0 all the way to 1, 1, 1, 1. Alright, it will be 16 possible values. Alright, if I didn't say, I just want to say. Because what I'm doing now is doing in terms of a 3-bit ADC. 3-bit ADC, if you go to 2 to the power of 3, is actually equals to 8. Okay, so therefore your 1 volt divided by 2 to the power of 3 is actually equals to 0.125. Alright, so that's not what I've been saying in your this one over here. It should be wrong. Alright, because this is actually 3-bit, 2 to the power of 3. Alright, so if it's a 4-bit, it's 1 volt. Alright, 1 volt divided by 2 to the power of 4, which is 1 divided by 16, which is 0.00625. Okay, so it's not 0.125 lah. But anyway, the more bit you are, the more refined your resolution will be. Alright, that's just the thing. Alright, so over here is just saying that 1 volt divided by 2 to the power of 3. So if it's 50 volt, then you're gonna 2 divided by 3, you will have different stuff. So 2 to the power of 3 tells you how many possibility values can you represent for your 50 volt. How many possible values can you represent your 50 volts, things like that. Alright, and the error, the quantization skill is this. The error is just taking the analog one, the blue color one, alright, minus away the digital one. Alright, so you'll have this thing over here. I think, yeah, I don't know, leave you to think about it. But anyway, not very important, I think. Hopefully not, because I'm not planning to do that. Alright, and linearity of the ADC. So over here, this is actually so over here what we are doing is a linear system. It's a linear ADC. However, sometimes you may not be a linear one. It may be something like this, right? As we have shown you, this is a non-linear system. It's a cosine curve, right? So it's a non-linear one. So you're gonna talk about linearity error, because sometimes the analog signal may not be a linear one. It may be a sine, cosine wave, things like that. Alright. By the notes he say is that for example, if you want to amplify your signal, alright, he's still talking about linearity. Alright, if you want to amplify your signal, not all the signals can be amplified. Alright, not all the signals can be amplified. Alright, and therefore some of the signals may not be amplified. So for example, this is the particular signal, quantization signal. Alright, so some of the signals can be amplified, but some of the signals may not be amplified. What am I drawing? For example, if you want to amplify this particular signal, alright, then you amplify it by this step. Alright, so if you were to draw it out, it's still a linear line. But however, sometimes it may not be exactly the one that you are seeing. It may be something like this. When you amplify already, some of the signal is amplified, some are not amplified fully. Alright, some are amplified, some are not amplified fully. So therefore the overall curvature may be something like this. Alright, so it's not very linear, you see. So comparing to that, if you were to take a look, it's not very linear, you see. So this is something that he's trying to say lah. Alright, so the linearity of the ADC. Okay, hopefully this is pretty clear. Then your offset is your 0 analog signal. Is standard one, he say, is remember your weighing scale. Sometimes you have the bar right at 0, but if sometimes when you step on the you never step on the weighing scale, the bar is actually some values already. Alright, so this is something like a 0th offset. Alright, so this is something that you need to consider. Alright, as an offset error lah. Alright, offset error, I repeat again, normally if you look at the weighing scale, alright, it should be at 0 when you didn't step onto the weighing scale, right? But however, when you didn't step on the weighing scale, the bar itself doesn't show 0, but somewhere over here, maybe like 0.5. Alright, so this is like an offset error. Alright, so because you didn't set it properly and things like that. Alright. Nonetheless, you also have a inaccurate reference voltage. Alright, you may you may input a different voltage and things like that. Alright, and then you may also have a different noises in your analog signal, so you may cause your system to read wrongly and things like that. So these are the four. So I think it's a good question when they ask is that what are the error source. You can say is linearity, offset, inaccurate reference voltage, noise, and last but not least the quantization error. Alright, and things like that lah. Okay, so quantization error, just to recap also, is that it's just to say that it is error because it doesn't correspond to your actual analog signal. For example, actual analog signal is a straight line over here, your linear line, right? However, because quantization breaks it down into steps, so therefore there will be an error between your analog and your digital, and so this is why it's called an quantization error, or your digital or digitization error, or whatever thing that you want to call it. Alright, so beside this quantization error, you have 4 other errors. So this is something that you need to digest. So I think, yeah. So next video we'll talk about see. Before I go into that, I want to say that for the key components to read analog signal, you have a V in and then you have a reference signal. So if your reference signal is wrong, you have an error. Alright, and then in your signal conditioning, you may have a alliancing issue, so you require a low pass anti-alliancing filter to convert your ADC analog to digital. Alright, then you will go to your microcontroller. So overall, this is how the thing is being seen. Alright, so you may need to understand that V in, your low pass filter, your V reference, your ADC, and your microcontroller. Alright, so in between you may have some noises. I don't know where it is coming from. Alright, but at least you need to understand all this stuff lah. Okay, so I'll leave you to think about it for this little stuffs, and I will go into signal conditioning, where you're going to condition your analog signal and things like that. So see you in the next video.